in this domain. It's fantastic, folks. I mean, when we all were working on this, we had no idea the world is going to change this way.
Right. Yeah, indeed. No, it's really cool that it's happened, actually. Yeah. Manya Ghobadi is a professor in the EECS department at MIT. So her research focuses on optical reconfigurable networks, networks for machine learning, and high-performance cloud infrastructure. Manya has received several prestigious awards for her research already, including ACM SIGCOMM Rising Star Award, the NSF Career Award, and several Best Paper Awards like at MLSUS, at ACM IMC, among many others. So thank you very much, Manya, for joining us today.
Thanks for having me.
Hi, Manya. Thank you for joining us. So we want to start with you maybe telling us a little bit about your background and how you become a researcher in reconfigurable data center networks.
Sure. Thanks, guys, for having me. This is a really interesting area. It's very close to my heart to think about reconfigurable networks in general. The way I got involved with reconfigurable optical data centers was kind of accidental. I received my PhD from University of Toronto about 10 years ago, and my research interest was mostly on traditional wired data centers, TCP, congestion control algorithms, etc. Then I joined Google as a software engineer, and through my experience within industry is where I realized the importance of traffic patterns and the physical layer that interconnects different servers. So after Google, I joined Microsoft Research, and there where I started a large-scale study of optical fiber networks in Microsoft's backbone. And that was the first time that I started to really think about and understand the importance of the physical layer and how it interacts and how it impacts the performance of the entire cluster.
How does data center traffic actually differ from other types of traffic, like internet traffic or enterprise network traffic? Can you please elaborate a bit on that?
Absolutely. This is a very challenging question to answer with one sentence, but I'm going to give it my best. The way to think about data center traffic is most of the traffic is generated through the servers that are communicating with each other, as opposed to the internet traffic, with the most of the traffic is generated from users communicating with services, say search or YouTube. The big challenging aspect of data center traffic is that there's a lot of jobs inside of a data center, say indexing the entire web or storage traffic. These are basically background jobs that are occupying most of the data center traffic, and they have very unique characteristics. They may be coming at bursts, they may be consisting of short flows, and they may be coming at predictable or maybe even unpredictable times. Whereas the internet traffic is very homogeneous and based on the human behavior. Like in the morning, people wake up, they start searching or watching videos, and maybe by noon, there's a bit of a peak. And then around lunchtime goes a little bit up. And then by the afternoon, everybody starts to watch Netflix. This is a very human pattern. But data center is challenging and interesting. It's challenging because there's no human pattern that we can impose, but it's interesting because once you go a little bit deeper into applications, different applications do expose some patterns, some familiarity. And so we can't take a scenario or a solution from internet and then just directly apply it into data center and hope that everything works. We have to really understand the traffic pattern of different applications within a data center and then design the network accordingly.
Can you give an example of such a pattern or application so it will be easier to understand?
Absolutely. So one of the recent applications that my group has been focusing on is machine learning. Think about a machine learning training job, say training a ChatGPT model. This model is massive. It takes months to train this model, but the traffic pattern is very predictable. There is a batch of data that is going into the machine learning model for training. The model is trained, and then the gradients are updated, and then the next batch of data is loaded into the model. And so iteration after iteration, thousands of iterations until the model converges. But throughout this entire month, we can actually predict the traffic pattern, which server is communicating with which other servers, and in fact, by how much. So the traffic matrix is beautifully predictable and periodic, which makes it very suitable to think about whether or not we could adjust the topology according to the traffic pattern.
Can you elaborate a bit on this, how like network systems can leverage this type of patterns?
Absolutely. So think about a world where you have a traffic oblivious data center. This would be a data center that is built to support any type of traffic at any time. This is a good idea. It's a good idea when we don't know anything about the behavior of the application. And in fact, we tend to build our legacy data centers with this notion. So we build a data center that has equal bandwidth between every server pairs. But we may be missing opportunities of optimizing the topology or the data center's connectivity had we known that two servers are communicating more heavily with each other, say between the hours of 8 a.m. to 9. And so if you know the traffic pattern, you could plan and build the data center accordingly. And that way you can gain more utilization and more efficiency. The job can finish faster.
One of the most interesting project that tried to do it is Project Tor that you were involved in, and you mentioned it before. Can you tell us a bit about the motivation, or more about the motivation? What was the novel contribution, and some interesting information about it?
The projector project started when I was at Microsoft Research 8 years ago. And the idea there was that when you look at everything starts with a traffic matrix. This is basically the go-to data that me and my team, we start looking at when we are thinking about programmable networks or reconfigurable networks. And so we started taking some measurements from Microsoft's data centers. And back then, there was no machine learning in the data center. So this is actually legacy storage traffic. And so when you look at the traffic matrix, where servers, the amount of traffic between servers are plotted, and think of a heat map. When the color of each element in the heat map is the amount of traffic that is communicated between servers. When we looked at the traffic matrix, we found something kind of surprising. The heat map is not the same color throughout. What does this mean? If it's not the same uniform color, it means that the traffic is not everybody to everybody with the same amount. The traffic actually has some pattern. Traffic is not just uniform, random, everyone to everyone, all to all. So we started thinking about what should we do if the traffic matrix has some really high communication pairs and some scattered low communication pairs. What are the opportunities there? What we found is that if you build a complete traffic oblivious network, you're basically either wasting a lot of bandwidth because not everybody is communicating with everybody at all times, or to save money, you may have to oversubscribe your data center, which means that you'll probably have congestion somewhere in your data center. So the whole idea is to adapt. Look at the traffic matrix and adapt. Can we adapt? That's the big question. is there a technology that enables us to adapt, to look at a traffic matrix and then accordingly build or reconfigure? Even better is to reconfigure the topology. The traffic matrix at this point in time has the behavior, but then if you look at it maybe an hour later, the traffic matrix might slightly change. So the whole idea is, instead of building a static topology based on one traffic matrix, can we bring in some reconfigurability into the data center so that depending on the observed traffic matrix, we can actually change the topology?
And how did you do it in Projector?
The idea in the projector was to use a free space optical interconnect. The thought there was to use the air as the medium, basically. And instead of literally putting cables and then reconfiguring the cables using what is called the 3D MEMS optical reconfigurable switches, we just use air as the medium, and then we use mirrors to literally reconfigure the connectivity between racks of servers. And the reason we chose air as the medium was mostly scale. It's still a good idea to use 3D MEMS optical switches, but at the time we were most focused on having a really large scale data center and being able to support a large scale. What we realized was that these 3D MEMS technology, they're just having a limitation in terms of port count. And in order to break away from that port count limitation, we thought about opening it up. It's almost like the idea is that you have a switch, but now think about opening that switch up and then installing the mirrors into distributed sets of on top of every rack. And that way, we're literally shooting laser up in the air and then using a series of mirrors. We call it a disco ball because it looks like a disco ball. We shoot laser to each little mirror of the disco ball, and then those little mirrors reflect the light towards the destination.
Good.
So how often do we need to adapt our data center?
Very good question. And different people, different service providers might give you different answers. In the fundamental way to think about this is to look at the application and then understand the requirements of the application. So I can give you a couple of examples. For instance, back to the ChatGPT example we were talking about earlier.
Mm-hmm.
What we show in a paper called TopoOpt is that actually for machine learning, it's fascinating. We don't really need to change the topology that often because of what I told you. The traffic is so stable and predictable that you could change the topology right now, start training ChatGPT and not touch the topology at all for another month. Okay? But if you have a different type of traffic, for instance, storage or indexing the internet, it is possible that the topology or the traffic matrix changes frequently, even within a second. And so you might have to change the topology more frequently. The key point here is to have a balance between the reconfiguration latency, the time it takes to change these mirrors, and the time it takes to shoot laser up. You have to have a balance between that and the reconfiguration time. For the projector paper, for instance, it took roughly 10 microseconds to change the mirrors. And so you could even change the topology within a few milliseconds. The key idea is to not burn too much time in the quiet reconfiguration period and try to utilize the effective data center most of the time.
Yeah, very interesting. So how did researchers build upon Projector, and how did the field evolve since you published that paper?
The way I think about this is that we as a community together started to take reconfigurable networks more seriously, not just on the building or experimenting side, but also thinking about theory. I don't think Projector was a big turning point in this area, but it was a contributor into a holistic set of researchers to try to think about this as actually a graph theory problem. It's a very nice, well-defined problem with a lot of interesting limitations that make the problem attractive, both from a theory perspective and from a practical perspective. In Projector, we were very much concerned about the practical aspects, but even there, we had a challenging theoretical problem of assigning these lasers to photodetectors without causing any mismatch. Like two lasers cannot point to the same receiver because that's a question, basically. And so what I really enjoy watching this field grow is that how it started even before Projector. We took it with a one design point, and then the field is continuing. And in fact, now it's totally entered into the machine learning world. And there has been many publications from Google and from other companies that are suggesting to use reconfigurable optical technologies for machine learning clusters.
Very interesting. And so what do you see as, also as a networking expert, but also you mentioned the theory, so you can talk on both dimensions. What do you see the next main challenges ahead to grow this field more?
I've been thinking a lot about how to bring the theory and the experimental or the practical limitations together. We've been attempting this for a few years, and I think perhaps the challenge that hasn't been solved yet is, from a practical perspective, there's a port count, optical loss, and reconfiguration latency. These
what about the impact about the other networking layers?
The other, you said?
The other networks layers, like transport layer,
I see.
routing, how does this comes into the picture?
The way I think about this is that every dimension, every layer we add, adds to the dimensions of the problem. And so let me start with an example test. Let's say that we have a traffic matrix and we want to find an optimal topology for it. So there's two dimensions to this problem. This is already NP-hard. Now, if we add routing and say placement or scheduling on top of this, or congestion control on top of this, problem grows, becomes massively more interesting, but also infinitely more challenging. And with every layer of dimensions that we add, we are making the problem even more challenging. However, the opportunity of optimizing actually grows as well. And so I've been thinking about this a lot. We should not fix one dimension and optimize another dimension. We shouldn't fix, say, routing and then optimize for a topology. The right way is to co-optimize all of these layers and dimensions together. But this is massively challenging, and this is where we could use some theory to help us to perhaps have an alternating optimization formulation, or a way of thinking about how can we navigate if there's an optimal point in a multi-dimensional space. How do we navigate and move towards this optimal space instead of landing in a local optimal place?
All right.
Do you also see opportunities for reconfigurable networks in the wide area setting, or is it mainly, or where will it involve, like also maybe towards other type of networks or in other parts of the data center? Are there any opportunities in those directions?
Good question. Perhaps the next opportunity to bring in optical reconfigurable networks in wide area would be private WANs for data center operators. Say Microsoft owns their own data centers and there's traffic between these data centers, say from Boston to New York,
Yeah.
to London. So that is an opportunity because the service provider owns everything and they know the traffic pattern. And so they could leverage this human behavior, for instance, and borrow some bandwidth from East Coast to West Coast overnight and give that bandwidth to the Europe side. The internet side, like the Comcast network, for instance, the network providers for the internet, that would be more challenging, but I'm optimistic. The thought is programmability brings opportunity for efficiency. And so I wouldn't be surprised if a service provider who owns links and is able to observe traffic pattern would decide to add programmability into their network for the sheer purpose of bringing in more efficiency and having better utilizing their network, basically.
Very interesting. Thanks a lot, Manya, for your time and
Thank
sharing
you.
all your insights and perspectives with us. It was really interesting.
Sure,
Thank
thanks
you
for
very
having me.
much.
Thank
It was
you.
very interesting.
Happy to, guys.